Hey guys, Rosado here. So, got a question about solving one of these problems right here, where you have to calculate the magnetic force that a moving charge experiences in a magnetic field. So before I just go through the equation and show you how to solve it, a little bit of background. So it is a moving charge in a magnetic field. So if the charge itself isn't moving, then it won't experience a force from that magnetic field. But if it is moving, then it is always going to experience a magnetic force. But the amount of force depends on a few things. First, look at your equation here. Looking at this tells you everything that it depends on. So right here we have Q, and Q stands for the charge. So the amount of force the charge experiences depends on how much charge there is. Second, V is for velocity. So how fast the charge moves determines how much force it's going to experience as well. So that's why I mentioned it has to be a moving charge. If it wasn't moving, its velocity would be 0. And if you plug 0 in this equation, you're going to get 0. And then, of course, it depends on the magnetic field itself. B is the symbol for the magnetic field strength. So the stronger the field, the more force you'd be expecting. And then we have sine of theta, which is just kind of sitting there and seems a little random, but here's why it matters. In the last video where I talked about the right-hand rule, I kept saying that they had to be perpendicular to each other. And the reason I kept saying that is because if they're perpendicular, they experience the maximum amount of force that they can. Perpendicular means at right angles to each other, and a right angle is 90 degrees. So if they were perpendicular, you would plug a 90 in here for theta. Well, sine of 90, you may know, is 1. So what that means is this number is going to be as big as it could possibly be. Because if the angle is less than 90, if I change it to 75, I now have a number less than 1. So now I'm going to get less force than I could have if they were perfectly perpendicular. And it's going to keep going down all the way until I get to 0. If it's at a 0-degree angle to the magnetic field, it's going to experience 0 force. Right here, this charge is at a 0-degree angle to this magnetic field. They're parallel to each other. They're going the same way. So this magnetic field does nothing to this charge. This guy, however, he's at a 90-degree angle. Notice this little square here. So they're telling you, hey, this is a right angle. This is 90 degrees. He experiences the maximum amount of force. This guy is off at some weird angle, so he's experiencing some smaller percentage of the maximum force. And here's where your equation comes in. We can actually figure out some numbers. Well, let's start plugging stuff in. F stands for force, obviously. Over here on the right is where I'm going to type these things in. So F is my force, and that equals the absolute value of Q. Q is my charge. Charge is measured in coulombs. That's right here. So 5.0 funny looking U C, and the C is coulombs. Well, you might remember that funny looking C because we've used it before. That is mu. And before we were using it as the coefficient of friction. Well, in this use case, this mu actually means micro. So 5.0 microcoulombs is actually really small. I mean, the word micro should hopefully be making you think of small things. So this is not 5 coulombs. I cannot just type a 5 in the equation and move on, because that would be wrong. This, when you have times 10, or sorry, when you have mu, that means times 10 to the -6. So micro anything means times 10 to the -6. And you have to put that in there because otherwise you're putting in a much larger number. You can't just put 5. So we have Q. V is velocity, and it just says straight up, it's moving at 1.8 times 10 to the 6th meters per second. Well, that's easy enough. 1.8 times 10 to the 6 meters per second. Then it wants B. B is the magnetic field strength, and it says to a magnetic field of 1.2 times 10 to the negative 5 Tesla. 1.2 times 10 to the negative 5 Tesla. And then I have sine of theta. Well, theta is an angle, and there's only one angle listed anywhere here, 30 degrees. Now, a couple areas that might trip you up on this problem. Number one, use your parentheses. Notice I have parentheses around every single term here. You may think, okay, cool, I know exactly what I'm doing, and type them in your calculator correctly, but without the parentheses. Your calculator might see that and go, oh, you want 6 times this number and then raise it to that power? It's going to get the order of operations wrong. Please put parentheses around each term. Otherwise, you're just asking your calculator to do something wrong for you. Second, make sure it's in degree mode. This is 30 degrees, not 30 radians. So make sure it's in degree mode. They usually default to radians. So make sure it's in degree before you try to do this problem. All right, so this right here is what I'm going to type in my calculator over here. So 5 times 10 to the negative 6, 1.8 times 10 to the 6, 1.2 times 10 to the negative 5 times sine of 30. And all that equals 5.4 times 10 to the negative 5 newtons. So my answer is 5.4 times 10 to the negative 5 newtons. This is the amount of magnetic force that this charge is going to experience by being in that magnetic field. It would experience more force if it was actually perpendicular to the field. So if it actually looked more like this, this is what our charge is doing though. It's off at this weird 30-degree angle. If it was perpendicular, this would be a bigger number. And then one more thing about the right-hand rule from yesterday. So there was something that I neglected to share with you guys. So when I talked about the right-hand rule, I showed you something like this. Here's the current, and then I called this the magnetic field. Well, the dots are telling me the magnetic field is coming out of the page. I compared them to like the head of an arrow shooting out at you. Well, this is not the only way the magnetic field could look. I just showed you an example from Edgenuity where they're just arrows that are going straight along the page. They could also look like this. These X's actually mean the opposite of the dots. So these mean going into the page. Dots coming out, X's going in. To continue with the arrow analogy, these arrows are like the back end of an arrow. You know how it's got the feathers on the back of it? This is like the back of the arrow going away from you. You would see the feathers and it would look kind of like an X as it travels away. So this means into the page. Dots mean out of the page. So into the page, out of the page. And this can be for anything, not just the magnetic field. The current could go into the page or out of the page. The force could go into the page or out of the page. Anything could. It just so happens magnetic field is usually what we use it for. All right, hopefully that clears up the right-hand rule a little bit more and helps with that magnetic force calculation that they gave you in Edgenuity. If there are other questions, of course, please post them in Google Classroom or email them to me. Be sure to like and subscribe, and I will see you guys later.